Even if all processes in production are clearly structured and regulated, just one unnoticed defect on the surface can lead to serious financial losses. A single ruined photomask isn't just a delay, it's hundreds of thousands of steps, all over again. A single flaw on a silicon wafer will be repeated on every subsequent layer and become part of the entire microchip. And a microcrack in the paint coating will trigger the gradual destruction of the material. Good afternoon, I am Marina Lobach, the scientific supervisor of the MAGUS project. Today, I will show you a tool that helps specialists detect such artifacts before they turn into problems. The MAGUS Metal 650 inspection microscope. This is an upright metallographic microscope with a large stage. It can be used in scientific laboratories as a full-fledged metallographic microscope for studying the microstructure of metal alloys in bright field, polarization, dark field, and Dai-G mode. But today, we will focus on its inspection capabilities, on the design solutions that make it possible to work with extended surfaces of thin samples. First and foremost, this includes the wide range of stage movement and the fine focus adjustment. As an example, let's consider an integrated circuit manufactured on a silicon wafer and see how the microscope is used at different stages of its production. The production of a microchip is a complex process. Hundreds of technological operations and dozens of photolithographic layers form the structure directly inside the silicon wafer, layer by layer, with nanometer precision. Each stage requires visual inspection. Any defect is replicated in subsequent layers and leads to rejection at the final stages. That is why optical inspection microscopes are used at every stage of production for quality control: surface frequencies, layer alignment, detection of microcracks, and lithography defects. Only upright microscopes are used for working with silicon wafers. In upright microscopes, the objectives are positioned above the stage, and the surface being examined faces upward. This arrangement prevents the working surface from coming into contact with the microscope stage and eliminates the risk of scratches. Light from the lamp is directed onto the sample through the objective, reflects off the surface, and returns back into the objective. The objective forms a magnified image and directs it to the eyepieces or to a camera. Now let's look at which microscopy techniques are used for inspecting silicon wafers and what defects they can detect. 4 main methods are available for MAGUS metallographic microscopes: bright field, dark field, polarization, differential interference contrast, or DX. Bright field is the basic inspection mode for general assessment of surface cleanliness and integrity. Polarization increases contrast and reveals anisotropic defects in dielectric films. Dark field is effective for detecting small particles and inclusions, scratches, and mechanical defects in photomasks. Differential interference contrast is used for analyzing microrelief and minimal height differences. By combining bright field and dark field, polarization, and DIC, the specialist obtains a complete set of tools for quality control at all stages of integrated circuit production and for inspecting photomasks, allowing defects to be detected before they lead to rejects or to an expensive process rollback. In the production chain for integrated circuit inspection, each stage uses its own observation methods, which is why the series offers different configurations. All models in the series support bright field and polarization. This is the basic set for most incoming and intermediate operations. Models with the BD index additionally support the dark field method. Models with the DIC index support the differential interference contrast method. This approach allows each section to be equipped accordingly, with exactly the tool required to solve specific tasks without overpaying for unnecessary features. On the screen are examples of how different microscope configurations are distributed across production areas. The table shows typical application options and helps to navigate the equipment selection for specific workstations. The final choice of configuration is always determined by the requirements of the technological process and the inspection tasks at this stage. In this video, we demonstrate the microscope in operation on real production samples. The footage shows defective silicon wafers removed from the technological process. Such samples are used for demonstration during training, as well as for validating visual distinguishability, defects, and for developing observation techniques. Let's move on to the microscope's design. The standard package includes a stand, a trinocular head with eyepieces, a revolving nosepiece with objectives, a stage, as well as modules for additional research methods. The heavy stand is made as an almost monolithic structure. All elements are integrated into a single frame, with only the visual head installed separately. This design ensures maximum mechanical stability. The massive frame dampens vibrations and reduces play when switching observation modes. Inside the stand is the focusing mechanism. The coaxial focusing mechanism combines coarse and fine adjustment, tension adjustment, travel adjustment, and coarse focus lock. The fine focus, with a step of 0.7 microns, allows for precise focusing on mirror-polished surfaces and distinguishing minimal height differences. These height differences are typical for the early layers of microchips. This is critical when searching for defects after CMP, monitoring topography, photoresist, and detecting thin residual films after etching. The stand is equipped with a stage featuring coaxial control knobs and a travel range of 204 by 204 millimeters. Such a working area size allows for easy placement and inspection of large samples with precise positioning and the ability to return to specified coordinates. Wafers of various diameters are used in microelectronics manufacturing, from small formats to industrial sizes of 200 and 300 millimeters. The main advantage is that wafers up to 200 millimeters in diameter do not need to be moved by hand. The entire surface can be examined simply by moving the stage. For 300 millimeter wafers, sequential viewing of individual zones is used. A 5-position objective turret is mounted on the stand, turned away from the observer. Therefore, the space above the stage remains completely open. This solution is convenient for inspection tasks. The operator can always see which objective is in the optical path and does not risk touching the sample surface with it. The microscope is equipped with plan achromatic objectives with a parfocal height of 45 millimeters and an extended working distance, which ensures safe operation. Samples do not come close to the front lenses of the objectives. The specifications are indicated on the body of each objective. The type of correction, PLL, plan achromat, focal length, magnification, numerical aperture, tube length, infinity, as well as the supported method, BD or DIC, are all indicated. The color coding corresponds to the international standard and indicates the magnification of the objective, so the required objective can be easily identified at a glance. The basic set includes magnifications of 5 times, 10 times, 20 times, 50 times, and 80 times. Additionally, 40 times, 60 times, and 100 times objectives are available. Please note that microscopes operating in dark field mode are equipped with special objectives marked BD. They have an annular gap between the optics and the body and function properly in both bright field and dark field modes. The mounting diameter and thread of these objectives differ from models designed only for bright field, so when choosing additional objectives, it is important to consider compatibility. The illumination system is built into the stand and provides full lighting adjustment according to the Kohler method. The lamp is centered along 3 axes and the field and aperture diaphragms are factory centered with the option for additional adjustment. For working with polarized light, a polarizer and analyzer are introduced into the optical path. The polarizer rotates 360 degrees, allowing precise adjustment of contrast and polarization orientation. Further adjustment comes down to selecting the brightness. If necessary, light filters are used to increase contrast. In the MAGUS Metal 650BD model, the illuminator includes a built-in dark field unit. Mode switching is done with a handle. Bright field and dark field illumination, visual head and eyepieces. The microscope is equipped with a trinocular visual head with interpupillary distance adjustment from 48 to 75 millimeters and an adjustable tilt angle, 30 degrees, which ensures comfortable operation during prolonged inspection. The standard package includes 10 times eyepieces with a 22 millimeter field of view and long eye relief. It is convenient to work both with and without glasses. The eye cups protect against side light. The eyepieces have a mounting diameter of 30 millimeters. Diopter adjustment is provided on the left tube. Additionally, eyepieces with magnification from 12.5 to 25 times are available, and a 10 times eyepiece with a scale. Digital visualization. The digital camera with software is purchased separately and is installed in the vertical tube using the SEMON adapter. The kit includes a 1 by lensless adapter, which is suitable for sensors about 1 inch in size. For cameras with smaller sensors, we recommend 0.5 times or 0.65 times adapters, which increase the field of view and make it easier to work with large surfaces. The light path selector directs the image either to the eyepieces or to the camera port, thereby eliminating stray light. The software allows you to display the image on the screen, perform measurements, save data, and stitch frames together for analyzing large surface areas. We have seen that. The MAGUS Metal 650 combines the capabilities of a full-fledged metallographic microscope and an inspection tool for working with large format thin samples. It provides stability, high focusing accuracy, and a wide working range. It allows you to detect particles, surface variations, relief, film defects, and photolithographic artifacts at various stages of production. The flexible configuration of the model makes it possible to choose the optimal solution for specific inspection tasks without unnecessary functionality. If you want to see how the microscope works with real samples and in the modes you need, we invite you to the MAGUS demo hall. Thank you for your attention and see you next time.